an FYI for everyone, you are in listen-only mode, but we will have a question and answer session at the end of today's presentation. So if you go to the dashboard on your GoToWebinar screen, you can type in any questions in the questions session. If you have any issues in terms of logistics with the actual program, go ahead and type your question into the chat, and we'll do our best to help you out with the system. Also, as a heads up, we will have a couple of poll questions during today's session, and you will be able to type in your answer to the poll questions, again, in the GoToMeeting dashboard. Now, today, Craig Campbell will be presenting an educational and insight presentation on bearing technology, and specifically looking at oil-free chillers and choosing the best options. Craig is a global product manager at Johnson Controls for York water-cooled centrifugal chillers. He works very closely with our product engineering teams and other global teams to improve our water-cooled centrifugal chiller product offerings. Craig is a Johnson Controls representative for the AHRI 550, 590 engineering and compliance committees. And without further ado, Craig, you can go ahead and start today's presentation.
Thanks, Jill, and thanks everyone for joining us today. So going over a quick agenda for today's meeting, we're going to review centrifugal chiller bearing options, and we'll go through the different types that are available in the marketplace today. Oil lubricated ball bearings, and when I refer to ball bearings, that's typically just a broad term that would cover ball bearings or roller element bearings that are oil lubricated. We'll also look at fluid film oil bearings, refrigerant lubricated ball bearings, magnetic bearings, and then we'll go into a deeper dive into oil-free options, and then we'll follow up with a case study example. So as an intro into the different bearing options, just wanted to show a Navy submarine. So York successfully introduced magnetic bearing technology in 1998 in the York Navy systems, and it's been used in over 125 critical Navy applications throughout the world. So it's very important that the right technology is chosen for these type of applications, because if you don't have a chiller and it's down and it's not operating, you can't open a window to reject that heat. So let's move on to bearing options. On the left-hand side, you'll see the traditional oil lubricated systems. So you have a oil lubricated ball bearing and also a fluid film oil bearing. And on the right-hand side, you'll see the oil-free systems. In the top right-hand corner, you'll see the refrigerant lubricated ball bearing, which is very similar to the oil lubricated ball bearing, where it uses refrigerant instead of oil as the lubrication system. And then in the bottom right, the only one of these that is truly lubrication-free is the magnetic bearings. So when we look at oil lubricated systems on a chiller package, looking at both the oil lubricated ball bearings and the fluid film oil bearings, which are used today in traditional applications that we've seen on chillers for decades, you'll see on the right-hand side a chiller schematic, and everything shown in the orange color is the bearing lubrication oil circuit. So required for these systems, you need a oil reservoir to hold the oil, the reserve oil, a pump, or you will need system pressure differential to move the refrigerant, and then you also need a heat exchanger to control the temperature of the oil, and then finally a filter prior to the oil going back into the compressor motor assembly. So if we move on to refrigerant lubricated ball bearings, this is a relatively new type of offering in the marketplace, and it is oil-free. So in terms of CO2 reduction, there is a little bit of CO2 emissions reduction just by not having oil in the system. However, when you see the great opportunity for CO2 emissions, it's going to be in the chiller efficiency overall. These are typically hybrid ceramic ball bearings, and they have reduced mechanical friction losses, so there is some increased efficiency just from a total chiller system operation standpoint. However, there is still regular maintenance. So if we look to the schematic to the right and look at the lubrication system for the refrigerant lubricated bearings, it's very similar to what we were looking at on the oil lubricated system. So we still need a reservoir for the lubricant. You still need a pump to create that pressure differential. A heat exchanger is still required to make sure that there's precise control of the refrigerant operating temperature prior to it going to the bearings, and it still requires a filter. So there really isn't a difference from a chiller package layout other than there's no oil in the system. So this system still requires regular maintenance. So there's still refrigerant level monitoring that needs to be controlled to ensure that the refrigerant reservoir is charged enough. If there are additives required for the refrigerants, that would need to be monitored and checked as well. And there's still the routine inspection for the filter and replacements over certain intervals of operation. There's also limited operating range. So because refrigerant is used as the lubricant, there are still some limits that would be applied to maximum compressor speeds. Also, it's similar to what you would see on a oil lubricated system. These bearings would still have a L10 bearing life. So that would be, on average, the life of the bearing, how long it would last through run hours. And you still have concerns about contamination, so that's why there's still a filter there, and contamination can significantly shorten the life of the bearing. Typically what we see on the refrigerant lubricated bearings is very little to no warning when a failure occurs, so it's very difficult to predict when you may need to do a bearing inspection or tear down or replacement. Failure occurs pretty quickly, so there's very little opportunity to do advanced maintenance or a scheduled shutdown and tear down. We also find that refrigerants show poor lubricity and sensitivity to temperature changes. So typically, when refrigerants and oil are mixed to lubricate the bearings, there's not as much concern for flashing of the refrigerant. However, when you remove the oil completely from the system and still have a lubricated bearing used in the system, without precise control of temperature, so not having a subcooled refrigerant, there is a risk of having the refrigerant flash in the bearings, which would completely eliminate all the lubrication and could increase or decrease the life of the bearing. And this is also a relatively new and experimental type of application for this type of bearing, so there isn't a lot of history or run hours throughout the industry using refrigerant lubricated ball bearings on chillers. So moving on to magnetic bearings. So magnetic bearings, like the refrigerant lubricated bearings, are oil-free. However, the magnetic bearings are the only lubrication-free bearing technology. So this increases durability. There's no contact, there's no metal-to-metal contact, so there's no mechanical friction losses, which increases the efficiency of the package. And there's also a theoretical infinite lifespan because there's no wear and tear on the bearings themselves. When you look over to the schematic of the chiller, you can see the entire system for lubrication is removed. So it's a very simple design from a maintenance standpoint, and the bearings are designed to last the life of the chiller with no scheduled maintenance or routine tear downs to check to see if there's any wear or potential failure coming in the near future. So less components essentially leads to less service and less to maintain. So just a quick overview of magnetic bearings. The magnetic bearings support the load using magnetic levitation, so there's no contact between the shaft. And this is a proven technology that's been used in critical applications, like I've mentioned earlier on the Navy systems. And it's not a very new technology. We first saw patents coming out around World War II, and then in 1974, the publication Magnetic Bearings: Optimum Design and Application is pretty much the basics and the basis of what's used today in magnetic bearing technology. So there hasn't been a big shift in the technology since the 70s. So as we put all these systems side by side, simplicity is really the key. When you look at the oil lubricated bearings and the refrigerant lubricated ball bearings, there's really no difference between the system setup. So there's still a reservoir, the heat exchanger, the pump, and the filter, whereas the magnetic bearings do not have all of those additional connection points and components. So from a system complexity standpoint, the magnetic bearings have the least amount of complexity when you're looking at all the components and the maintenance of those systems. So let's take a look at a cost comparison. We have the oil lubricated on the left, the refrigerant lubricated ball bearings on the right, and the magnetic bearings. So it's very clear the first cost of the mag bearings are the most expensive. However, we've seen significant reduction in costs over the past decade of magnetic bearings, which is why they're becoming more commercially available, and we're seeing them used in many different applications, not just chillers. From an oil lubricated ball bearing system to a refrigerant lubricated ball bearing system, there is a slight premium for the refrigerant lubricated, but nothing very significant. So we do have the added first cost of the mag bearings, but as you start looking at the total system and the maintenance and the potential downtime, that's where we see customers really valuing or really understanding the value of magnetic bearings. So there's no filter replacements, there's no filter checks, there isn't a pump, there's no heat exchangers, there's no additives, and there's no scheduled bearing replacement that would result in downtime to do an inspection, and then also any labor required to take apart the chiller and make that change. So if we look at it from a technology standpoint, all of these are bearings, just like all of the pictures at the bottom are phones. And while you can call the two telephones on the right-hand side wireless, that doesn't make them truly significant equivalents. So you're not getting the operational capabilities like you do on a smartphone, like you would or compared to a wireless landline phone. So it's easy to say they're both wireless, just like it's easy to say, both those bearing types are oilless, but only one of them is lubrication free. So moving away from the bearings and taking a look from the total system layout of why it's important to look at it from a chiller standpoint, we'll see how the mag bearings truly provide an advantage in a chiller system. So on the right-hand side, you'll see a schematic of the York YMC² drive line. And the York YMC² utilizes a permanent magnet motor with active magnetic bearings. And you can just see a cutaway of the the centrifugal impeller there as well. But the YMC squared is allowing the chiller to operate using the magnetic bearings in a very wide operating range to maximize efficiency. So the bearings do not have as much of a operational limit that you would see on a traditional system that requires system pressure differential or a pump or cooling requirements for the lubrication that the lubrication system requires. It also has very fast startup time, so if you have a critical application that needs a fast restart upon a power failure, or if you have a process that needs to come on very quickly, there is no startup time required for the lubrication system to make sure there's adequate system pressure differential. So that eliminates a lot of time required to do a startup. It's also environmentally responsible, so there's reduced greenhouse gas emissions, not only just due to the removal of oil in the system, but also the added efficiency that comes with no mechanical contact with the bearings. And it's a very reliable technology that's used in many applications, both military and commercial throughout the world. So another benefit of the magnetic bearing system is the sound levels. So you'll see across this infographic, the pictures, the York YMC squared chiller on the left-hand side has a dBA level of as low as 73 using the AHRI 575 rating method. So in comparison, just so you have a baseline, a dishwasher in your kitchen would be about 80 dBA. So if you can imagine yourself in your kitchen with the dishwasher running, you're still able to have a conversation in the room. It might be a little nuisance, but the YMC squared chiller is significantly quieter than that. And we find a lot of customers are amazed at how quiet it is when they're standing next to it. They're not even able to realize that it's running unless they go up and touch it. So when we compare that to a traditional chiller, centrifugal chiller would be around 85 dBA, a blender would be up at 90, and a truck would be at 95. So very impressive sound levels for any applications that may require reduced sound levels because they're close to occupants within a building that do not need to be disturbed. So when we look at the capabilities of the mag bearings in terms of a operating envelope, what you'll see on the left-hand side is entering condenser water temperatures that would go in from the tower into the chiller, and then across the bottom you see percent load for the chiller. And what we have in the inside line, the inside dotted white line, is other magnetic bearing chiller manufacturers, the operating range that they're showing valid operating points for their package offering. And what we'd like to highlight is the capabilities of the YMC squared, the York YMC squared. So the York YMC squared is able to take higher entering condenser water temperatures. We're able to overspeed the impeller with the magnetic bearings to overcome that system pressure differential, the buildup in the condenser, to avoid surge and stall that may be experienced on other chiller packages. And we're also able to use low entering condenser water temperature to improve the efficiency of the total system while utilizing low tower water temperatures that may be available in certain areas of installations throughout the world. And we're also able to utilize extra low entering condenser water temperature, and we're going to touch upon that a little further. So typically on traditional systems, you would see minimum entering condenser water temperatures anywhere from 65 to 55, but now we are able to go well below that. So if we look at part load efficiency then and now, previously, prior to the advent of putting variable speed drives on chillers, a constant speed chiller at part load would be able to reach about a 0.4 kW per ton at part load. Then when adding a VSD to the centrifugal chiller and you're able to slow down the motor, we were seeing across the industry kW per tons as low as 0.2 at part load. Then as magnetic bearing technology started to come into the marketplace, that started to push the part loads using both the mag bearing and the variable speed technology. You know, we were almost, as an industry, getting below 0.2 kW per ton at part loads, breaking into the 0.1s. But now with the York YMC squared, we're able to get down below 0.1 kW per ton with very low entering condenser water temperature at part load points. So with that, let's move on to a poll question. And the poll question is, what has a greater impact on chiller efficiency? Load or lift?
So I've activated the poll question. You can go ahead into the dashboard under the poll section and enter in your response.
Okay, so taking a look at the results, we have 28% as load and 72% as lift. So the correct answer is lift, and we'll go on to walk everyone through this. So when we look at real-world efficiency, lift versus load, on the left-hand side you'll see kW per ton, and across the x-axis you'll see percent load of the chiller going from 20% up to 100%. So if we were to maintain a constant 85 entering condenser water temperature and see a load reduction on the chiller from 100% load down to 16% load, in terms of kW per ton, that would be a 15% reduction in kW per ton. However, if we keep the load at 100% and we go from a 85 entering condenser water temperature down to 75 degrees, that's a 24% reduction in energy. And if we still maintain 100% load and reduce the entering condenser water temperature down to 55, that's a 59% reduction in kW per ton. So just a 40% reduction in load only gave us a 15% reduction in kW per ton, but just reducing the lift across the chiller by reducing the entering condenser water temperature provides about a 59% reduction in efficiency. So very big opportunity to save energy for customers by utilizing low entering condenser water temperature. So if we look at real-world efficiency in terms of IPLV, what you'll see here are the 4 IPLV points that are used to create the single point metric that's often used to compare chiller efficiency. So each point is weighted differently. The 100% point at the design 85 entering condenser water temperature represents 1% of the total chiller efficiency for IPLV. And then there's the 75% point at 75 degrees, and then both the 50 and 25% points have 65 degrees entering condenser water temperature. So as you can see, while this is a meaningful metric to compare like-for-like chiller technologies from efficiency standpoint, it really doesn't represent the true efficiency capabilities of a chiller. If you're able to utilize lower entering condenser water temperature, you'll see much different results in the chiller efficiency and the system efficiency. So we're going to go to our next poll question. And we'll give a minute for everyone to respond. Okay, so what is the lowest entering condenser water temperature a chiller can handle? And I did briefly show this earlier on the operating range, so it looks like some of the participants did catch it. So it is 36 degrees entering condenser water temperature, and we'll talk through that in the upcoming slides. So now when we jump back to the kW per ton curves that we were showing earlier, at 85, going from 100% load to 60% load with 85 entering condenser water temperature, we were only able to get 15% improvement on kW per ton. But if we're able to go all the way down to 36 degrees entering condenser water temperature, you can see down in the lower left-hand corner, we're able to get below 0.1 kW per ton. So let's take a look at a specific chiller rating at 500 tons. So this is a YMC squared chiller at standard H or I conditions. So 5444 on the evaporator and 85, 94.3 on the condenser. The IPLV you'll see here is a 0.3068. And then when you look at the minimum entering condenser water temperature report, you can start to see the full operating range or the full map of the chiller. So down the left-hand side, you'll see entering condenser water temperatures starting up at the design point at 85, and then it increments down all the way to 36 degrees entering condenser water temperature. And across the top, you'll see the load going from 100% or 500 tons all the way down to 10% load. So what we want to focus on is this area in the bottom right-hand corner. So we're looking at chiller loads at 60% and below, and we're looking at entering condenser water temperatures at 50 degrees and all the way down to 36 degrees. So if we look at 50% load or 200 tons for the chiller, utilizing 45 degrees entering condenser water temperature, it's at a 0.089 kW per ton. So below that 0.1 kW per ton that we talked about earlier. And while producing 50% of the chiller load, we're running that chiller at 22 kW. So when you look at a traditional constant speed chiller that we referred to earlier, when running at a 50% load and 65 degrees entering condenser water temperature, which would be the points that would be used for the IPLV equation, that efficiency is a 0.4563 kW per ton. So when we look at the 0.08 versus the 0.45, that's an 80.5, or that's an 81, almost an 81% efficiency improvement just by reducing the entering condenser water temperature while still providing the same amount of tons to the system. So let's take a look at a case study. We're going to first just go through a traditional design with a base chiller and a water side economizer. So we'll just do a quick overview of a schematic. So in a traditional system, you would typically see a base chiller, and for this example, we chose a ASHRAE 90.1 Path B compliant chiller with a variable speed drive. So the full load was a 0.585 with an IPOV of a 0.38. And then that's also being used with a water side economizer, or commonly referred to as a free cooling heat exchanger or plate and frame heat exchanger. So here's our simple schematic. It's the towers connected to the chiller and also the water side economizer. So we're able to provide chilled water to the building load. So typically in mechanical cooling mode or in the summertime in chiller mode, the water side economizer will be off, and the chiller would be providing 100% of the mechanical cooling requirement to the building. In the wintertime, the system would enter into a free cooling mode where the water side economizer would provide all of the free cooling or the required cooling to the system. But what is the kW per ton of a water side economizer? For this example, we'll just assume that it's free. Since we call it free cooling, that's what we'll refer to it as. And the reason a lot of people thought, or it was always referred to as free, was because to run a traditional chiller with constant speed prior to having variable speed drives when water side economizers were widely used, the chiller efficiency was a 0.45 kW per ton at 50% load, and the chillers were limited to a 65 degrees entering condenser water temperature. They weren't able to operate below that. So there were significant savings when looking at water side economizers with many operating hours with low tower water. But with having a water side economizer and a traditional chiller, there's always the shoulder months. So which one should be used in these scenarios? It's not really cold enough to use the water side economizer. Getting that tower water can't get you all the cooling you need in the shoulder months, and the tower water is too cold for the traditional chiller to run. It's below 65 degrees, but it's not low enough to provide 44 degrees to the system. So which one is used in the facility? And there's a lot of changeover problems between going to from one system to the other. So let's take a look at just how the traditional system's set up. So typically you would have a AHRI design chiller with an evaporator flow rate of 2.4 GPM per ton and a condenser flow rate of 3 GPM per ton. And your design point would be 85 degrees entering condenser water temperature with a supply of 45 degrees on the chilled water, or 44 degrees on the chilled water loop. Now with the YMC squared, we're able to utilize low tower water. So in this example, it's still able to run and provide the full building load at 45 degrees entering condenser water temperature. And on the evap side, it's still providing 44 degrees. So there's no reduction in the chilled water set point. There's no reduction in the flow on the condenser side. So it's not head pressure control. It's not variable flow on the evaporator side. We're doing constant flow. So in this scenario, if you had a water side economizer, you still wouldn't be able to provide 44 degrees leaving chilled water because the tower water isn't cold enough to pull down the evaporator or the chilled water loop below 44 when the return is above 45. So in this system, like we showed earlier, when using 45 degrees entering condenser water temperature at 50% load, the YMC squared chiller efficiency is a 0.089 kW per ton. But we're still able to go even further below 45 degrees. We're actually able to run inverted. So inverted means the entering condenser water temperature is less than the leaving chilled water temperature. And the YMC squared chiller is the first chiller in the world to continuously operate in an inverted duty. So in this scenario, the chiller is still operating the same way it would at 85-degree entering condenser water temperature or 50-degree entering condenser water temperature. It's still providing mechanical cooling. We're still having the refrigerant complete the refrigeration cycle while running the compressor. So let's take a minute here and go to our last poll question. How often throughout your experiences do installations experience waterside economizer changeover issues? Okay, we're closing the poll up. So the results here that we have tallied on the screen, we have 0% for never, we have 30% for sometimes, 42% for often, 15% for always, and 12% for not applicable. So how can the YMC squared chiller operate in an inverted duty or inverted manner? So as we kind of walked through on the presentation already, the oil-free operation, so having the magnetic bearings completely eliminates the concerns about oil or refrigerant return to the bearings. We don't have to worry about system pressure differential or having a pump or oil migration to make sure that the bearings are properly lubricated. We also have the permanent magnet motor, and the advantage of the PM motor is the chiller is able to adjust the speed to operate across that wide range of conditions. So on a traditional motor, you would have a turn down of a 2-to-1 ratio. However, with the speeds that we're operating on the permanent magnet motor, we have much more turn down ratios, where we have a 4-to-1 turn down ratio. And we also have a variable orifice. So this is kind of the main component that connects the whole system together. So the expansion valve between the evaporator and the condenser, by having a variable orifice, allows adequate refrigerant flow from the condenser to the evaporator to control that differential between the two circuits to ensure that the evaporator doesn't starve and the condenser stacks up and the chiller shuts down on low evap pressure. So now we're going to go into an engineering study that we had completed by an outside third-party consulting firm. And for this study, various load profiles were looked at, but we're going to focus for this presentation on a 1,000-ton new office building using two 500-ton chillers, and then the system has a 200-ton internal base load. We also looked at variable primary flow for the chilled water circuit and constant speed for the condenser loop, and optimized VSD tower control. So we looked at 3 different locations, Chicago, Dallas, and San Francisco. And the modeling assumptions are shown below. It was a chillers were selected based upon ASHRAE 90.1, the 2013 requirements. And the chilled water plants are modeled according to the Appendix G baseline with variable speed chillers and primary only variable flow chilled water loops, and it was simulated with eQuest. So when we look at the plant annual energy costs, you'll see the energy costs for the base chiller and water side economizer in orange. In Chicago, the total operating costs were just over $70,000, 98 in Dallas, and 125 in the San Francisco Bay Area. And that system, utilizing a base chiller meeting the ASHRAE 90.1 requirements with a water side economizer, was then compared to a York YMC squared chiller without a water side economizer. So looking at the total plant annual energy cost by utilizing very low entering condenser water temperatures, we were seeing significant savings when utilizing the York YMC squared chiller. So anywhere from just over $1,000 to almost $14,000. So that's a look at just the operational costs. So the York YMC squared was providing energy savings. But if we look at the first cost of a water side economizer system, once you take into account the first cost of the plate and frame heat exchanger, all the insulation, piping and accessories, and the controls, and not even accounting for routine maintenance to maintain the water side economizer, doing yearly cleaning and ensuring that it's operating properly, those costs add up very, very quickly. So if we look at the upfront costs across the three locations, we see a range of $150,000 to over $200,000 just for a water side economizer system to be purchased and installed. And then when we compare that to the energy savings, there wasn't a scenario for the office building where there was a payback for the water side economizer. So not only are you eliminating those first costs, and you're also getting annual energy savings, and not even having the added expense of routine maintenance across the water side economizer. So if we look at other advantages other than the first costs and the energy savings, more space can be used for whatever the client needs. So there's no mechanical footprint required because the water side economizer was removed. That allows for future expansion room if the building's going to grow, to add more chillers or larger chillers or other mechanical equipment in the space. There's fewer water leak points because there's less piping. There's no valves. There's no bypass or isolation valves that could leak over time. There's no routine maintenance required for cleaning the plate and frame heat exchanger, and it does give you the possibility of increasing the building load in the future if you have a tight mechanical space. So here's just a quick screenshot of our dashboard that we have for connected chiller services, where we're able to monitor chiller performance and chiller operation if the client chooses to request that service. So here's an installation we have at a pharmaceutical research lab in the Northeast region of the United States, and you can see we have entering condenser water temperatures down below 50 degrees. They're hovering right around 40, 48, 45, and the chiller's maintaining about a 47 degrees leaving chilled water set point. So we do have this operating in throughout the U.S., and we have customers that are just thrilled about the operational savings. So in summary, we went over the 4 different bearing options for centrifugal chillers, and we looked at oil and oil-free options, and they all have their unique advantages. There are 2 options for oil-free bearings. However, there's only one lubricant-free bearing option, and that's the magnetic bearings. And we feel that the York YMC Squared is the best choice for oil-free bearing operations. And with that, I'm going to turn it over to Jill, and I want to thank everyone for for joining us today.
Yeah, thank you so much, Craig. And again, thank you everyone for joining the webinar. We're going to get to questions and answers in just a moment, and there have been a few that have been asked in the system. But if you have a question, please go ahead and go into the dashboard and type in your question. We'll get through as many of them as we can. I just wanted to let everyone know that we will be sending all registrants an email with some additional information and links and a recording of this session. But just to let you know, if you go to york.com and do a search for magnetic bearing, you can find additional information about the York YMC squared as well as magnetic bearing technology. And then the other thing that I wanted to mention on the next slide is that this is just one part of various series that we have on different webinars from Johnson Controls. And again, in the follow-up email that we send, we will include a link to the registration information. But coming up on Thursday, May 11th, there's a webinar that will be around refrigerants, busting refrigerant myths within the industry and specifically for chillers. So if you're interested in learning more about that topic, please look in your email and access the link for the registration for that webinar. Now we'll move on to a couple of questions. A few that have come in already. One question someone has is, what capacity range is possible with the YMC squared chiller?
So at standard AHRI conditions, the YMC squared is available from 165 tons all the way up to 1,000 tons.
Great. We had another question that asked, how is it possible to operate in an inverted manner while still circulating the refrigerant?
Yeah, so that's a question that we do get fairly often when we are talking about inverted and minimum entering condenser water temperatures. Typically, from a customer standpoint, the customer needs to know what those temperatures are in terms of the water circuit. So the entering condenser water temperature and the leaving chilled water temperature usually have to have some type of differential at various chiller loads. However, from a chiller manufacturer standpoint and from a system standpoint for just completing the refrigeration cycle, we're still concerned about having a pressure differential to make sure that the refrigerant is moving from the condenser into the evaporator, so we aren't starving the evaporator and shutting down on a low pressure system safety to prevent the water in the heat exchangers from freezing. So even though the temperatures of the water are inverted in these scenarios, we still have a pressure differential between the two shells to ensure that we have adequate refrigerant flow between the two to complete the refrigeration cycle.
Thank you, Craig. A few more questions are coming in. One is asking, how much time is actually available with operation below 55 degrees?
So that's going to vary widely based upon any specific location or chiller installation. However, there are significant amount of hours available well below 65 and 55. We would recommend that for every chiller installation or application that a full weather analysis would be reviewed to see how many hours are available at any of the temperatures. But even places like California and Florida have well over 10% of their hours are below 55 degrees, which is significantly more than the 1% of hours that the chiller would see at the design point. So we feel it's important to look at the entire operational map that the chiller will be able to, so that you can review all the different operating points and maximize your efficiency by looking at everything that's available for the system.
Thank you, Craig. Another question is asking about in terms of retrofit. So, if someone has a YMC² chiller installed, can these chillers support the inverted operation, or is a new system required?
That's a great question. So there is no requirements on the chiller package itself to run in an inverted. You just need to start supplying colder tower water, turn it down, and let the system run.
Great. More questions are coming in. We have one here asking what portion of energy savings can be attributed to magnetic bearings?
The magnetic bearings themselves, depending on what they're replacing, you can see savings in the anywhere from 3 to 8%.
All right, we have a question here asking us about air-cooled systems and magnetic bearings, and if magnetic bearings are offered or will be offered or should be offered on air-cooled chillers.
Yeah, so there are some air-cooled offerings available in the marketplace. However, from Johnson Controls' perspective, the air-cooled market tends to be more of a first cost-sensitive market. So we have a lot of different chiller technologies, from variable speed screws to air-cooled scrolls that are available that are very low cost and also are extremely efficient. So when you look at the first costs in terms of the installation costs, and then you take into account the energy savings, we find that a lot of customers aren't willing to pay the premium for the amount of efficiency they're getting. However, we're always evaluating technologies in the marketplace, and whenever we feel that that threshold is overcome, I wouldn't be surprised to see an offering.
Okay, thank you, Craig. We have just a few more. We have a question asking about, is the cost of a YMC² chiller comparable to the base chiller cost? I believe this is in reference to what was presented in the case study.
Yeah, so when looking at the case study and what we went over earlier in the presentation, there is a premium for magnetic bearings. Just the inherent first costs of the system are higher because of the technology. But when comparing the total system costs of a chiller and a water side economizer, the first cost of the YMC² chiller is significantly less than it would be to buy a traditional chiller with a water side economizer. So the savings of eliminating that water side economizer is an immediate savings to most applications.
All right, we have time for a few more questions. We have one here that's asking, what is the maximum lift capability of the YMC² chiller?
So the YMC² has a lift, typically what you'd see on a single stage centrifugal compressor would be about 70 degrees of lift, and that's similar to what we see on the YMC². It can handle slightly higher than that based upon the speed and the way that we do our capacity control. But we're also able to use very high entering condenser water temperatures if we have a very high entering evaporator temperature. So the YMC² is also available as a heat pump for installations that can provide an elevated heat source to use that for beneficial heating purposes.
Yeah, we did just get a question, specifically asking if a heat recovery can be added to a YMC² chiller.
Yeah, so we do have a heat pump option, so it would still be a single circuit or single water circuit on the condenser side, not a dual circuit with multiple connections. But you could still use the condenser for heat reclaim or for preheat through the system.
All right. We have a question here asking if the YMC squared chiller with chill water temperature supply at 28.5 degrees. I think we're asking in terms of like a glycol-based system, if glycol is a possibility and that kind of extended capability. If that's a possibility.
Yeah, so the YMC squared is able to handle leaving fluid temperatures with glycol or brine down to 10 degrees Fahrenheit.
Okay, we have a question here asking, is there an accelerometer kind of thing available in magnetic bearings? And then could we also comment in the case of oil lubricated bearings?
I'm sorry, I didn't get the first part of that. Can you please repeat?
It's asking, is there any accelerometer kind of thing available in magnetic bearings? And then if we can comment on the oil lubricated bearings. I'm not 100% certain. Maybe some of the individuals who asked, if you're still on the line, if you could provide some clarification.
I'm assuming the accelerometer for the mag bearing would just be measuring the vibration of the motor. That would be my guess. So the mag bearing system is constantly monitoring the position of the shaft at very high sampling rates. So anytime there's excessive vibration that would occur on that shaft, then we would go into a safety shutdown. However, because the bearings are very robust, we do not see a lot of vibration, and you see that, you experience that through not only just touching the chiller, but the sound itself. There's very little vibration across the entire system. In terms of accelerometers used on oil lubricated bearings, yeah, those are used typically as a warning system. The vibration is increasing, and that there could be issues with the bearings that would require a teardown or an inspection to make sure that everything's okay.
All right, I think we have time for one more question, and then you know, there were a couple questions that we weren't able to get to, so we will be sending off a file with some additional answers to the questions that were asked. And then again, you can reach out to us if you do have any other questions through the follow-up email. So the last question here is the compressor motor located outside of the refrigerant loop?
For the York YMC squared chiller, it is a refrigerant cooled motor, so it is inside of the chiller package. It's a semi-hermetic motor.
All right, great. Thank you so much, Craig, and thank you all again for attending. As I said, we'll be sending a follow-up email, so you can access the recording and also get some additional information. Thank you so much, and have a great rest of your day.
Thank you.